In the last video, we discussed what a volt was and how we could apply it to half reactions. Well, what you can see on the right-hand side of your screen is a list of standard half reaction potentials. And what you should take away from this is things at the top end of the table here. These are things that like to be reduced. Fluorine's very reactive, and it will seek to make a fluoride ion with just about anything it comes into contact with. So positive voltage here means very spontaneous. Likewise, things at the bottom, like lithium ion, not very reactive at all. In fact, lithium ion fights to become lithium metal. It's very hard, or it's a very unwilling participant in a reaction. You really have to cram a lot of energy into getting a lithium ion to become lithium metal. So this list of table shows us things that like to be reduced and things that don't. Now, one of the nice things about this is if we take a reaction like, for example, lithium ion and an electron going to lithium metal, we could write the reverse reaction for it, and what we would find is that lithium solid likes to go to lithium ion and an electron, and when we reverse a reaction, what happens is the cell potential simply flips its sign. Now, each half reaction we measure is reference to the hydrogen ion undergoing reduction to hydrogen gas. And it was somewhat an arbitrary choice, although it was also somewhat not an arbitrary choice, as having it defined as being equal to 0. It was selected as being 0 because thermodynamics had the same reaction as being defined by 0. And so in keeping with our thermodynamic data, we find that, well, it just makes sense to call the same 0.0. Even though we're measuring it in terms of different units, you have to have something be equal to 0, and, well, why not that reaction? So what we can do is then we can begin to separate out our oxidation and reduction reaction and form what's known as a voltaic cell. A voltaic cell involves a spontaneous redox reaction in which electrons are transferred from one material to another using a wire. And this wire, as you can see in the voltmeter here, involves electrons going from zinc all the way over to copper. So what's going on? Well, the zinc solution in the zinc metal is slowly dissolving. That is, the zinc metal is losing its electrons, and the zinc ion, which we would have right here, goes floating out into solution. Well, when that happens, the electron moves across the wire over to the other electrode, where we have a piece of copper metal now sitting with an extra electron on it. And what happens is when a copper ion comes into it and it sees that electron, it sticks to the plate. So in this particular voltaic cell, we have zinc dissolving and we have copper precipitating out onto its metal. Well, while the electrons move across a wire, what happens is that nothing would continue to occur after that first couple of electrons passed, because now you would start having a buildup of charge on one side. Here there would be, on the copper, there would be lots of negative charges, and in the zinc side there'd be lots of positive charges. And so we need some way of balancing that. Well, what we do is we add a salt bridge. So right here we have basically a U-tube filled with some sort of strong electrolytic solution like sodium nitrate. Something that's not going to react and completely dissociates when put in water. And what happens is that the sodium ions, or the cations, begin to migrate towards the side with all the negative charges, and likewise the negatively charged nitrate moves towards the side with all the positive charges. And so it creates an overall neutral solution. Even though we're moving charges through it, we maintain electrical neutrality. Well, you can imagine that if you're building a battery, the U-tube is going to be quite fragile. And so one of the earliest changes to the voltaic cell was to replace the U-tube with just a porous barrier. And so our second generation voltaic cell looks something like this, where we, rather than have a U-tube, we just have a semi-permeable membrane which allowed the sodium nitrate to move across, but not necessarily the zinc and the copper ions. So when we assemble two materials to undergo a redox reaction, we measure the cell potential, or we can predict the cell potential by taking the reduction potential and adding it to the oxidation potential. So, for example, with our zinc-copper example, what we can do is we can go look up what the reduction potential is for copper, which we just go back a few slides, and we'll find copper is sitting somewhere right around here. And we see zinc is down here. Now these are both reduction potentials. And remember, in order to have a redox reaction, something must be oxidized and something else must be reduced. Well, when we write the balanced equation for our zinc-copper electrode, what we find is that the zinc oxidation potential, because it's being oxidized, has a positive 0.76 volt contribution, and that the copper reduction potential has a negative 0.34 volt contribution. So in determining the cell potential for this, we find that the cell potential for a zinc-copper voltaic cell has a potential of 1.1 volts.